Okay, so here we're going to do problem 8, and then we're going to kind of use it as a way to launch us into problem 9. All right, so we're flipping a coin 3 times, and I just want to start off by pointing out that there are 8 different possibilities we could get. We could get all tails, or we could get tails, tails, heads, or we could get tails, heads, tails, or we could get tails, heads, heads, or we could get all of these options here, with the only change being that all of these tails also are heads. Okay, those are our 8 options. I'm gonna shrink this down so we can keep the question in scope here. Oh, didn't mean to shrink it down that much, but that's okay. Okay. So first off, we want to figure out, well, what's the probability that we get no heads here? That means we get all tails. Well, the probability that our number of tails equals 0, sorry, our number of heads equals 0, that's what we care about, is going to be equal to the probability we get tails on the first flip is 0.9, and on the second times 0.9, and on the third times 0.9 again. So this will be 0.9 cubed. Okay. Things get a little bit more interesting when we look at one head, because now there's not just one way we can do it. We could get one head this way, we could get one head this way, or we could get one head this way. All right, and so the probability that our number of heads equals 1 is going to be, well, what does the probability of one of these things look like? Tails is 0.9 times 0.9 times 0.1, or this one would be 0.9 times 0.1 times 0.9, but in any case, we have 3 of them, and by rearranging our multiplication, we can get that it's going to be 0.1 times 0.9 squared. Okay, play that game once more with our 2 heads. Those are these 2 options. Probability of the number of heads being equal to 2 is going to be also, there's 3 options, except for now we have 2 of the two heads, which each occur with probability 0.1 times 0.9. That's our tail. And then lastly, all heads, sort of just like the first one, isn't too interesting. There's only one way that we can do this. 3, and this is just, there's sort of one of them, and it's going to be 0. Maybe I'll write that 1 explicitly, 0.1 cubed. And so you can see that the exponent on the 0.9 sort of counts down 3, 2, 1. It's always going to be 3 minus the number of heads, because that will give us the number of tails. And this exponent 1 sort of always matches the number of heads. So here we have a 0.1 to the 0, 0.1 to the 1, 0.1 to the 2, 0.1 to the 3. Okay, so you might ask, well, what's the pattern then with the number of times that this shows up? What's the idea here? Well, what we're going to think about, we're going to generalize this. So now let's say that we have more than 3 coins. Maybe we have 5 coins. And we want to know how many ways can we get exactly 3 heads. So here's how I'm going to think about this, is that we're going to have a bunch of buckets. In particular, we're going to have 5 buckets. And maybe we label these buckets 1, 2, 3, 4, 5. Okay, and the ways that we can get 3 heads is that we're going to pick the buckets one at a time. Okay, so maybe we start off, we pick bucket 4. There's 5 ways that we could pick our first bucket. Times, now we need to, this is going to be a head. Times, okay, now we're going to pick the place that our next head goes. Maybe that's going to go in position 1. So there's 4 choices for that. Now there's 3 choices left. Maybe we'll put it here. Okay, so that tells us that there were 5 times 4 times 3 ways we could place these heads. But of course, if we had started off in 1 and then gone to 4 and then gone to 5, that would have been the same thing. Or if we had started off in 5 and then gone to 1 and then gone to 4. And so we can ask, well, how many different ways are there to do this? And it turns out, for the order of picking the heads, well, you could choose any one of these to go first, say this one to go first, and then there's 2 options of what goes second. Maybe we choose this one, and there's only 1 option of where we laid down our third head. So that is 3 times 2 times 1. Sort of tells us the answer in an ordered way, and this tells us the answer in kind of an unordered way. And now this we oftentimes write as 5 choose 3, suggestively, because we had 5 boxes and we chose 3 of them to fill in. And the way that we're going to compute this is 5 factorial divided by 3 factorial times 5 minus 3 factorial. Turns out that this computation does the trick. Okay, so we're going to use this idea in the next problem, where our number of coins and our number of heads is different. But I want to point out that in this problem, in problem 8, we could say that the probability that the number of heads is equal to k, which, notice that's just a probability mass function there, is going to be equal to 3, because that's how many coins we had, 3 coins. We want to count up our number of heads, that's going to be k, times how many heads we get. So the probability of getting a head is 1 to the power of k, times the number of tails that we get, which is going to be, in this case, 3 minus k. Okay. And it's sort of no coincidence that all of these k's match, those go together, and it's also sort of no coincidence that all of these 3's match. Okay, and then these are the probabilities of our 2 different events. So we're going to use this, and we're going to do problem 9 with it.